was a bit of a short break. Now we will switch gears and talk about Ligand field theory. And those of you who have been trained in theoretical chemistry, they will think, oh my god, Ligand field theory, that's like grandma theory, and this is outdated, and why would I ever use Ligand field theory if I can use my Gaussian program or something like that? But that is missing an important point, and that's why I want to spend like a little bit of time talking to you about why you need things like Ligand field theory and how it can enhance in a very major way the results you can get out of very sophisticated quantum chemical calculations. And for that, I want to put up this slide here and talk about theory and chemistry for a little bit. So what I've now talked to you about in the last lecture is the molecular Schrödinger equation. And if you solve the molecular Schrödinger equation and say we would do it perfectly, you would get perfect numbers. And what do you do with these numbers? These numbers obviously have a big meaning, and it lets you predict the outcome of experiments precisely. And it was a long time ago where one of the pioneers of theoretical chemistry, Charles Coulson, I think was it, who said that, I mean, it's great if the computer understands the problem, but I want to understand it too. And there is an important lesson there to learn. It is the fact that we can compute something doesn't necessarily mean that we understand something. And so what we really do when we solve the Schrödinger equation in whatever like approximation scheme we have, we create numbers. These numbers can be incredibly useful, these numbers are important, but these numbers in themselves are not a theory of chemistry. They're simply numbers that you obtain for one individual molecule and one given nuclear configuration, not more and not less. But say if you have the question, like what really is it that governs the behavior of a class of substances, then of course you're at a loss, because you simply have like single numbers for individual molecules at fixed geometry. And so what you need then is a connection of that complicated microscopic theory to a theory of chemical language. Now, and that ultimately arises if you oversimplify that apparatus here to a point where you create a phenomenological level, model. And that model will be so simple that it can be phrased in terms of a very few quantities, and these very few quantities create a chemical language in which you can discuss trends among chemical series. Very typical for that is the theory of pi systems in organic chemistry. It is absolutely essential to organic chemistry that you have the concept of aromaticity and pi systems. It arose from a theory that's utterly oversimplified. But it is important to do that. And at the end of the day, all of these phenomenological models belong to effective Hamiltonians. Now that there are good effective Hamiltonians that have a very clean connection to like the rigorous apparatus here, there are less good effective Hamiltonians that have no clear-cut connection. The pi theory, for example, is one that doesn't have a very good clear-cut connection. Whatever it is, these things, these phenomenological models, they help us think chemistry, talk chemistry, and develop concepts. That's why they're so incredibly invaluable in bringing meaning and order to a large number of facts. So they shouldn't be dismissed on the account that they don't produce accurate numbers, but they should be praised on account that they bring order and meaning to chemistry. Without it, it's just a numerical exercise, it's a workout. And it's important, it's nice, it's great that we can do it, but it's not the end of the story. Yeah, so that is the important lesson here. So with that in mind, what is Ligand field theory? So Ligand field theory is a semi-empirical theory that applies to a class of substances, in that case namely transition metal complexes. It is a language in which we can cast and interpret a large number of experimental facts. And obviously it's a model that only applies to a restricted part of reality. That's the nature of a model. It's not a shortcoming. It's the intention of a model to only apply to a restricted part of reality. That makes it so valuable that you don't explain all of the world in terms of that model, but that part that you choose to want to understand, that is part of the model. So what Ligand field theory is not an ab initio theory, and it's not an ab initio theory that lets you predict the properties of a given compound from scratch. Yeah? So you cannot say, like, draw a given compound and then say what will be its precise properties, and which precise wave number will I have in absorption band, and which exact magnetic field will I observe a G value. But Ligand field theory lets you predict, say, the number of peaks you expect in an absorption spectrum. It lets you predict the general shape, say, of the EPR spectrum. But then it contains semi-empirical parameters that you would need to fit to the experiment in order to get a good numerical agreement. That's very different from the ab initio prediction that comes out of the quantum chemistry. The benefit that you get from Ligand field theory is insight because it's so simple. And in order to approach it, we will look at the periodic table. That is the biological periodic table. These are the elements that matter most for biology, and as you see, then, I mean, you're all inorganic chemists, so I don't need to explain to you the first transition row. And by means of the Aufbau principle, it is the 3D shell that starts to get filled in the first transition row. And it is the chemistry of electrons in these d orbitals that make the chemistry of the first row transition metal so incredibly varied and also so complicated. Now, when we start to fill in electrons, a number of complications arise. And I want to mention at least some of them, and the guiding principles, the ones that you really have to have in the back of your mind, and that connects very closely to what I've been talking about in the last lecture. And that is so easy to forget that it's worthwhile, like beating on the same nail time and again. At the end of the day, atoms and molecules exist in electronic states. These orbitals are great. These orbitals help us organize our thinking. At the end of the day, it is states that matter. These orbitals you cannot observe, also not the 3D orbitals in transition metals. As I said before, the states of an atom or molecule can be characterized by 4 criteria. And the first is the distribution of the electrons among the available orbitals. That is called the electronic configuration. Yeah? You simply say this orbital carries so and so many electrons, and that so and so many can be 0, 1, or 2. Then the overall symmetry of the state, if the molecule under consideration transforms according to any of the point groups, the total spin of the state, I'm coming back to that in a moment, and the projection of the spin onto the H. So that is exactly the same as what I've shown you before in the lecture. So this is what makes up an electronic state. And one important aspect of electronic states, and especially when it comes to transition metal complexes, is the total spin. Now, since spin is counterintuitive, and already the spin of one electron is counterintuitive, the spins of many electrons might be even more counterintuitive, but you will not be able to understand anything about magnetism if you don't deal with the total spin. So, how do you construct a total spin? So first of all, doubly occupied orbitals do not contribute to the total spin, because then the electrons are simply paired. The 2 bar magnets of the electrons are anti-parallel. Their magnetism annihilates each other, and so doubly occupied orbitals do neither contribute to the magnetic moment nor to the total spin. Singly occupied orbitals can be occupied with either spin up or spin down electrons. And these unpaired electrons can be coupled either parallel or anti-parallel to produce a final total spin S. Now, and here's the important thing that is easy to forget when you do an actual calculation. For a state with a total spin S, there are two S plus 1 magnetic sublevels or components. Yeah? And these are labeled with a quantum number m, and that m takes on values s minus 1, all the way down to minus s. That is important. That means at the level of the Born-Oppenheimer Hamiltonian, all of those two s plus 1 components for a state with a given spin s are there, are observable, and are degenerate. It is only when you turn on relativistic effects that, or magnetic fields, that this degeneracy is lifted. Now, all of EPR spectroscopy and enterospectroscopy lives off, and also magnetism lives off these magnetic sublevels that arise from the two s plus 1 components of a ground state with a given spin s. Now, when you draw these pictures here, where you distribute electrons with their spins among orbitals, where like an arrow up is a spin up electron and an arrow down is a spin down electron, you can figure out the m sub s quantum number by simply summing up all of the individual m sub s, small m sub s quantum numbers for each electron. So for example, here we have 3 orbitals, we have 5 electrons. So these 2 orbitals, these 4 electrons in these 2 orbitals are all paired, they don't contribute to the total spin. Now our total m sub s is just the same as the small m sub s of this electron is 1/2, so capital M sub s is 1/2. And since there is only one way to do that, the total spin s of that state must also be 1/2. Now, if all of your electrons are parallel, it's also easy. Like here, you have 2 unpaired electrons, so the total m sub s is equals to 1. And the total spin s must also be 1. Yeah, but it's only one component out of 3. Yeah, because this is a triplet state, and it also has an m sub s equals 0 component and an m sub s equals minus 1 component. Now things start to be a bit funny when you have electrons that do not couple to the maximum spin that is allowed by the number of unpaired electrons. For example, here you have 3 electrons in 3 orbitals. You have 2 electrons spin up, 1 spin down. Now you can say for sure from that picture that your m sub s is equals to 1/2. Yeah? So it's like 1/2 minus 1/2 is 0 plus 1/2 is 1/2. Yeah? However, from that configuration there are as many as 3 electronic states that arise. There are 2 states with a total spin of 1/2 and 1 state with a total spin of 3/2. Now, this one configuration here that actually translates cleanly to one Slater determinant, like it contributes in principle to all of these 3 states. Yeah? Now, the important thing is all of these states are observable, they're all real. Yeah? They're all real, they just don't couple to the total spin. Now, if you do a normal spin unrestricted, say, DFT calculation, you converge to something like that, and then the colleagues from physics will tell you, yeah, there is a spin wave here or there is a net magnetization, or God knows what it is, but it's completely missing on the point that this single electronic configuration creates 3 observable states. Yeah? And each of these 3 states has all of the magnetic sublevels. So both of the 2s plus 1/2 states have m sub s plus minus 1/2, so that's a total of 4. And the s3/2 state has 4 magnetic sublevels, so there are a total of 8 states that you can do spectroscopy on. Not just 1. That's important. Yeah? The subtleties of the total spin take a while to penetrate and come to grips with. So this is just a teaser for you to study that a bit more deeply. If we wanted to do that in detail, it would take us an hour or 2, which we don't have here. But it is more than meets the eye. That is what I want to tell you. Now, say we accept that there is a total spin, then what are the states that we can form. And I will talk about the states in transition metal complexes for the rest of the lecture, so it's useful to start with atoms. And in atoms, the states that can arise are best classified according to the atomic Russell-Saunders terms. And they are coming from, they're described by atomic term symbols 2s plus 1 capital L. Yeah, and so that S is the total spin angular momentum, the L is the total orbital angular momentum. So as you know, that orbitals in atoms, they carry angular momentum as well. The spin carries 1/2 unit of angular momentum, and the orbitals carry angular momentum according to the number of nodes that they have. So there is 0 in s orbitals, 1 unit of angular momentum in p orbitals, 2 in d orbitals, and so on and so forth. Yeah? And there are rules to construct the total orbital momentum in a very similar way as there are the rules to construct the total spin angular momentum. Now, all of these states that you can form from a given electronic configuration, these atoms, is real. And the fact that they're real and they can be counted and can be accounted for in a perfect way is proven by these atomic line spectra. So the internet is full of like tables of these atomic line spectra, and each one of these lines corresponds to one of the possible Russell-Saunders terms of the atoms. They all have been measured, they all have been cataloged, they all have been assigned, and they're all perfectly understood. It's an incredible resource to go to these tables and find out which Russell-Saunders terms can arise for a given ion. Yeah? These Russell-Saunders terms are actually called multiplets. And at the level of the Born-Oppenheimer-Hamiltonian, as I said, a state with spin S has 2s plus 1 magnetic sublevels or components. 2s plus 1 is hence a multiplicity. At the same time, a state with a total angular momentum L has 2L plus 1 components, and hence it is 2L plus 1-fold degenerate. That means that there is a total degeneracy of 2s plus 1 times 2l plus 1. Yeah? Now, for historic reasons, the states with L equals 0, 1, 2, 3, or 4 are given the symbols S, P, D, F, G. There is no logic in that. It is simply, you have to learn it because that's the way it historically arose from studying these atomic line spectra. Now, there are Hunt rules, actually Hund's rules, that tell you something about the energetic ordering of these terms. And for terms of given configuration, the one with a higher total spin S is lower in energy, and we understand that from the Hartree-Fock method that I've told you about, because there is the exchange integral that stabilizes states with parallel spin, and hence the states with higher spin S have more parallel spin electrons, and hence they are lower in energy. And the second Hund's rule says that terms with a given configuration and equal total spin have the higher angular momentum lower in energy. So that is the second Hund's rule. Now here I took some examples. Now you have the 5d orbitals here. You put one electron in, so you have a multiplicity of just 2s plus 1 equals 2. Yeah? So that is a spin 1/2. There are 5 possible ways to put that one electron into those 5 degenerate orbitals, so that must belong to an L of 2. And hence what you have here is a doublet D state. So you would have that in titanium 3 plus or vanadium 4 plus. Another second simple situation arises if you have 5 electrons in these 5 d orbitals that are all with parallel spin. So here you can count it out and must come to the conclusion that S is 5/2. And there is only one way to achieve that, so that must belong to an L of 0. So that is a sextet S state, as in manganese 2 plus or iron 3 plus. It is therefore that these ions are also called sextet S ions, because their atomic parent term is the sextet S state. Now it gets more complicated if you don't have the shell filled or half filled, as for example with 2 electrons in these 5d orbitals. Now if you have a parallel spin, then it's easy again. That's got to be a triplet state, but there are like still 10 ways to put these 2 electrons with parallel spin in 5d orbitals. And if you do the algebra right, that you certainly have learned at some point in your chemistry curriculum, you will find that this belongs to a triplet F and a triplet P term, both of which are observable, as in vanadium 3 plus or chromium 4 plus. Now that seems like a lot to learn, and you don't have to learn it by heart, you can look it up. But it's also, if you study it a bit, it's not that hard to do with pencil and paper. What helps you here is to know that holes create the same terms as electrons. So if you have 9 electrons instead of 1, that creates the same doublet D term as the 1 electron. So whether you want to think about holes or electrons, that's up to you. I personally tend to like to think about electrons because I can't picture holes, but electrons I can grip and handle. But in terms of counting the terms, the holes are as good as electrons. So now we have molecules, and molecules are not atoms, and the one thing that is most prominent when you go to molecules is that they don't have spherical symmetry. And so everything that involves the orbital angular momentum requires spherical symmetry. As soon as you lift the spherical symmetry, the orbital angular momentum goes away as a good quantum number. So the orbital angular momentum can no longer be used as like an ordering principle of these many electron states, but what you can use instead is spatial symmetry. So if your molecule has any symmetry, then it is group theory that tells you what the possible irreducible representations are under which each state transforms. I know that every chemistry student has to suffer through that at some point in time, so I will not do that here. I will simply remind you that a molecule can be classified according to the operations that turn the molecule into itself. These are symmetry operations, among which there are rotations, improper rotations, inversion, and reflections. And so to each of these point groups there belongs a character table, and these character tables has irreducible representations. At the end of the day, each of the states that can arise must transform according to the irreducible representations. Now, if you want to bring order to your notations, then I recommend the following, that you always, whatever you do, you use small letters that you reserve for orbitals or anything that you discuss at the 1 electron level, and capital letters that you reserve for states, hence that happens at the many electron level. Okay, and it is just because that the orbitals also transform under the irreducible representations, and then you can construct states of a given symmetry from the occupation of the orbitals that each for themselves transform according to their Fs. Now, in a nutshell, when we write a T term, then it's a triply degenerate level. An E term is a doubly degenerate level, be it many electron state or an orbital, and A and B is reserved for non-degenerate levels. So what replaces the Russell-Saunders term in atomic spectroscopy is now for molecules the term symbol 2s plus 1, the multiplicity, and then gamma, and gamma is the irreducible representation. So that as a short reminder of the formalism that we will need to label the states that arise. Now with that, I will give you like the most simple possible version of Ligand field theory that I can think of. So to start with, we have to see what drives the formation of a complex. And on the most superficial level, you have a transition metal ion that is typically positively charged, and then you have a ligand that is either negatively charged or has regions that are partially negatively charged, and hence there is an electrostatic attraction in there. For example, you have a simple ligand like ethylene diamine here that carries an NH2 group that has one lone pair, and the region of these lone pairs come with negative electrostatic potential, and so hence these are the hot spots for that ligand to attach to a metal. So far so good. That drives it. If that was initially made for bioorganic chemists, so there are really very few biologically relevant protein-derived ligands, and if you talk about nitrogen donors, you have a histidine or a lysine. For oxygen, you have tyrosinate, glutamate or aspartate carboxyl group, or an alcohol from serine, or an alcoholate if you deprotonate it. And sulfur, there is a thiolate, cysteine, and methionine, thioether. That's actually all. That is all that proteins have to offer in terms of coordinating ligands. There are a few external ligands, but overall it is absolutely stunning what nature manages in terms of chemistry and chemical reactions on the basis of a very restricted ligand set. And yesterday you have heard Frank Meyer and his heroic modeling efforts, and you see it is so hard to come up with anything that's close to nature, and nature does it with these very few ligands. Anyways, so that is something to marvel about, something to find out about. I'm sure that is something that some of you are at least into. So now there is also coordination number and coordination geometry. So it's the number of ligands that attach to a given metal, that is a coordination number. For coordination number of 3, you have either trigonal, pyramidal, or T-shaped complexes. Trigonal complexes transform under the point group D3H and T-shaped under C2V. For 4 coordination, you have either quadratic planar, T4H complexes, or tetrahedral, TD complexes. For coordination number 5, it is either quadratic pyramidal, C4B, or trigonal bipyramidal, D3H. And for octahedral symmetry, you have an OH point group. So that is the most common ones. Obviously, that is way too simple because, as a matter of reality, most molecules you're dealing with, I'm dealing with, are not that highly symmetric. But the important point is that they're approximately symmetric, and there are certain features in the spectroscopic and physical properties that you can recognize in these molecules, even if they don't conform perfectly to these point groups and don't conform perfectly through these coordination geometries. For example, even in proteins that are highly asymmetric, you have approximate coordination geometries that you can deal with. For example, you have, even if you have the same metal, like iron, you can have tetrahedral sides as in rhodopyroxene, approximately trigonal bipyramidal sides as in protocatechol and dioxygenase, approximately tetragonal pyramidal sites as in tyrosine hydroxylase, and approximately octahedral sites like in many, many enzymes like lipoxygenase. So that creates like the playground that the electronic structure problem is happening in. Okay? So to approach that, we will start very simply by looking at the shapes of the d orbitals. Now these are the shapes of the d orbitals, and we plot them in a coordinate system x, y, and z. Now everything that is red is positive, everything that is yellow is negative. So what are these plots? We draw like a surface around areas of the same function value, say 0.03 and minus 0.03. Yeah? So these are those things. There are obviously then these regions where there is a node, where the function value is 0. And for the xz, yz, and xy orbitals, that happens precisely on the coordinate axis. Whereas the dx squared minus y squared and the dz squared minus r squared orbitals, they have their probability amplitude located on the coordinate axis. Remember the interpretation that we gave for the many particle wave function, the Born interpretation. It is the square of the total wave function that matters. And so for the one electron orbitals that we're looking here, it is also the square that matters. So whether I exchange yellow against red doesn't really matter. And so if I square these things, then I get the probability distribution of an electron that is occupying one of these orbitals. Yeah? And so then for the xz, yz, and xy that is sitting between the coordinate axes, and for these two orbitals sitting on the coordinate axis. Now I make a heuristic argument about what happens if I put a transition metal ion with partially filled D shell into a ligand field. And I take a very physicist approach. Ligand field theory is a very physicist theory because we strip down these ligands to nothing but a partial charge or a point charge. Yeah? So let's say we create an octahedral ligand field, and then we have like one electron in those d orbitals, and we ask ourselves, what is the energy of interaction of the electron in the various d orbitals with that ligand field here? So obviously the negatively charged ligands produce an electric field and electric potential that is felt by the electrons in the d orbitals. Yeah? And that is repulsive because you have a negatively charged ligand and you have an electron, and that electron is repelled by the negative charge or partial negative charge of the ligand. Now the interaction is obviously not equal for all of these 5 d orbitals. And like if we draw arrows, we would say that the average distance of the electron in a dz squared orbital is shorter to the ligand because it's sitting on those coordinate axes relative to an electron that is occupying the xy, the xz, or the yz. That means that an electron that is occupying a dyz orbital is less strongly repelled by the ligands than one that is occupying a dz squared orbital. What that means is that the degeneracy, the 5-fold degeneracy of the d orbitals is lifted by the ligand field. And so if you do your group theory properly, we had the 5 degenerate d orbitals in the free atom or ion. They created a doublet d state, and now they split, and if you work out the mathematics, they split into 2 sets, a T2G set, because we're talking the octahedral group, OH now, that is triply degenerate and consists of the xy, the xz, and the yz, and a doubly degenerate set that is of EG symmetry, that is the x squared minus y squared and dz squared. Now you put one electron into those T2G orbitals, and you create a doublet T2G term. Yeah? So that is the ground state of a D1 system in an octahedral ligand field. Now you could work through the mathematics, and the mathematics really isn't very hard to do. Now, in a nutshell, so this is a charge distribution that the ligands create. If you take them as point charges, we have a delta function at the positions where these point charges are. And then you plug that in, and the charge distribution creates this potential. And in order to simplify the mathematics, you can expand that inverse distance in terms of spherical harmonic functions. You insert that into the potential, and you get an expression for the potential. And then it simply calculates the matrix of that potential over the d orbitals that has relatively simple expressions. You can diagonalize it, and that then creates the one electron scheme of those d orbitals in the ligand field. Now, that happens to be diagonal for an octahedral field, and you could then, by taking the difference between the expectation value of the ligand field potential over the EG orbitals minus the T2G orbitals, also come up with an expression for the splitting between these two orbitals. For historical reasons, that is called 10dq. And the expression that you would get for it is 5/3 times the charge on the ligand divided by the metal ligand distance to the 5th power times the 4th power of the radial operator over these d orbitals. That is all totally unimportant, yeah? Because none of that is anywhere realistic. You can go through this mathematics and you can like scratch your head with equations, but it really doesn't matter. Because if you plug in numbers now for these quantities, you get something that has nothing to do with anything you can measure. It's also something that gives you absolutely ridiculous predictions. And that is the point here. We're creating a model. And we're not creating a precise numerical theory. The precise numerical theory I've talked about in the last lecture. The one thing that this model predicts and that is meaningful and relevant is that these 5D orbitals split into two sets, an EG set and a T2G set, and they have some energy separation, 10dq. And whatever oversimplified expression gives that energy difference is absolutely immaterial. Yeah? So the purpose of a model is to be simple and transparent. If one over-elaborates simple models with complicated mathematics, one does something incredibly counterproductive. Yeah, so in principle what matters is this, and what doesn't matter is that. Yeah? Now that we've understood that there is that ligand field splitting, of course you want to know what the consequences are. And the simplest consequence, of course, is to try to come up with an experiment to measure it. And that experiment is optical absorption spectroscopy, because I told you it is looking into the chemical bond, and that means it is optical absorption spectroscopy that lets you measure these energy splittings. And of course you don't measure the splitting between orbitals, but you measure energy differences between states. You measure the energy differences between the doublet T2G state, the ground state, where there's one electron in the T2G shell, and the doublet EG state that arises from promoting that electron from the T2G shell to the EG shell. Now, if you put in a photon of the right energy, what you get is an absorption band. That absorption band is a bit funnily shaped, and we will later briefly comment on why it is so funnily shaped. For the moment, just pretend this is like one absorption band. It's centered around 20,000 wave numbers, so your experiment tells you 10dq equals 20,000 wave numbers. Okay? And in the early days of ligand field theory, that has been done a lot, and it has been done a lot for all kinds of different ligands. So this is actually the spectrum of hex-aquatitanium 3+. And chemists have went out of their way to synthesize many, many, many different compounds with many different ligands, and then want to order these ligands, and you want to order them into something that is called the Spectrochemical Series. And it is ordering those ligands according to their ability to split the d orbitals. And so there is, to the left of the spectrochemical series, ligands that lead to small splittings like iodine, sulfide, fluoride, and to the right there are ligands that lead to very large splittings, and this would be CO or NO or NO plus or CN minus, and in the middle there are ligands like H2O and NH3. Now there is something already that meets the eye that is fairly strange. And that is that OH minus, according to that spectrochemical series, is a weaker field ligand than H2O. And then you say, wait a second. My ligand field splitting should go with the negative charge on the ligand. And you would certainly say that the negative charge on the oxygen of OH minus is more negative than the oxygen in H2O. That's obvious, isn't it? Hence, that already shows you that something is very fishy with the explanation of the ligand field splitting that ligand field theory came up with. And at the end of the lecture, we will, of course, look at what that is. At that point, we take it as an empirical observation that there is a spectrochemical series. You can also translate that to biochemistry, but that doesn't matter for that lecture. Now, it has been one of the major triumphs of ligand field theory to take these spectroscopic measurements and be able to explain some thermochemistry with it. And that is the ligand field stabilization energy. That is something that is actually really very nice. So think about, you can measure the energy that it takes to take 6 water ligands and bring them onto a metal 2+ ion. Yeah, that is the hydration energy, and you can experimentally measure it. Now, the experimentally measured hydration energies for the first order transition metal ions, they're plotted here. These are the open circles. Now, if you would measure that and then you bring that data to your boss, then you say, oh, that wasn't a good experiment. This looks very bumpy. Then I either fit a straight line through it or repeat it. And you would repeat it, and it would send you back again and repeat it and repeat it. And then if you're a good scientist, at some point you say, look, I know my error bar. This data is real. It should mean something, despite the fact that it has a funny double bowl shape. Now, ligand field theory provides an explanation for that double hump shape, and that is the ligand field stabilization energy. So we've seen that all of these d orbitals are destabilized by the presence of the ligand field. Now, if you take the barycenter of the orbital energies for that ligand field problem, then the T2G orbitals are less destabilized by -2,5 over that ligand field splitting delta, whereas the EG orbitals are destabilized by +3/5. Yeah, that means relative to the center of gravity, an electron that occupies the T2G shell is less destabilized than the EG shell. And that is the ligand field stabilization energy. Now, if you have a single d electron, that is -2/5. You put a second d electron in, it's -4/5. Put a third d electron in, then it's -6/5. Now the fourth electron has to go into an EG orbital, then it goes down to -3/5, whereas the ligand field stabilization energy is 0. If you put the fifth electron in, namely at manganese 2, the ligand field stabilization energy is 0. And then you have the same again for filling the second half of the shell. Now, if you take the measured delta values for all of these complexes that you get from optical spectroscopy, and subtract these ligand field stabilization energies from the open circles, what you get are the filled circles. So now that falls on a perfect straight line. Now, why is that still sloped? That is still sloped because for each additional metal ion in the series, you obviously add a proton and an electron. That additional electron will shield the positive charge of the proton, but it will not shield it perfectly. That means that the effective nuclear charge of the metal ion seen by the ligand is increasing along the series. That is actually something very important to understand the periodic trends in the first transition metal series, is that there is an effective nuclear charge that is increasing along the series and is much larger for the late transition metals than from the early transition metals. So that is now a perfect explanation of this funny looking experimental data. There is an overall periodic trend that is modified by the ligand field stabilization energy that gives it that funny double hump shape. Has been one of the major triumphs of ligand field theory, and it makes you believe that there is something meaningful that this theory is able to predict. And it predicts, it explains a trend in chemistry among a series of compounds, just as I said at the beginning it set out to do. Now, life is not so simple because there is, as I told you, the situation that electrons repel each other. Now, as a simple recipe, you can think about that electrons that occupy the same orbital repel each other more strongly than electrons of opposite spin that occupy different orbitals, which repel each other much more strongly than two electrons that occupy different orbitals with the same spin. Yeah? And we talked about why this is so. So this is the difference between Fermi and Coulomb correlation, whereas here the electrons are just on average more closely. And of course, all of what I said about Hund's rules also applies to molecules as long as we talk about degenerate orbitals. And it also means that all of these terms that arise from distributing electrons among the available orbitals in atoms and ions also apply to molecules. As I told you, that is numerically, quantum chemistry is an uphill battle against the consequences of electron repulsion. In ligand field theory, this is not so. In ligand field theory, electron-electron repulsion is actually simple. And you can take care of it by just simply two empirical parameters that are the so-called Raka parameters, B and C, which you can simplify down to one parameter by recognizing that C divided by B is on the order of 4 to a good approximation, and B is on the order of 1,000 wave numbers. So for example, to get an idea of what the types of multiplets are that arise in transition metal complexes if you have more than one d electron, look at this here, 2 electrons in the T to G shell. If they're paired, you get a singlet state, and if you work out the group theory, then this is a singlet T to G state. If you have the electrons unpaired and have a parallel spin, that creates a triplet T1G term. If you work through the mathematics of ligand field theory, you will find that the energy splitting between these states is 6B plus 2C, so hence it's on the order of 40,000 wave numbers. That's substantial, although this is the same electronic configuration, right? So it's T to G2. And yet you have a series of states arising from it that are split by 40,000 wave numbers here. And that's quite a large energy. So it is more than just electronic configuration. It is the multiplet splittings that arise from the interelectronic repulsion that you absolutely have to take care of in transition metal complexes. So all of these one electron pictures that you have in organic chemistry, they really, really don't work in inorganic chemistry just because of this. Now, your orbitals are not really degenerate, but they're split. And that means you have the opportunity to have either high or low spin ground states. So what determines that? So say you have a D5 configuration. A high spin configuration would be one with all electrons with parallel spin. That obviously minimizes the electron-electron repulsion. Or you can have them in a low spin configuration where they're paired except for one, and all occupy the T to G shell in an octahedral complex. That obviously maximizes the ligand field stabilization energy. Now, which one will win? The answer is sometimes one wins, sometimes the other wins. And you can obviously now plot that as a function of just one parameter. And that is the ligand field splitting delta divided by the Raka parameter B. If that is small, meaning the ligand field splitting is small, then you have a weak field ligand, and the high spin configuration will be lowest in energy. Now, if delta over B is large, say on the order of 20 to 30, you have a strong field ligand, and the low spin configuration will be lowest in energy. That kind of makes sense if you think it through. I mean, these are, if you're a computational chemist and you have a given compound, you just stick it in the computer, and sometimes you will forget that there are alternative spin states that you should investigate if you want to find out what the ground state is, what the reactivity is. In ligand field theory, this seems like almost too trivial to even mention it, but that shows you how powerful that theory is in organizing your thinking. Yeah, and that's why it is so important to have an understanding of it. You just do better computations if you organize your thinking according to ligand field theory. So now we come to the very heart of ligand field theory. Now you have like all the tools in hand to understand Tanabe-Sugano diagrams, which are absolutely central to ligand field theory. Now, what is a Tanabe-Sugano diagram? It is a plot where on the x-axis you plot the ligand field splitting delta in units of the Raka parameter B. On the y-axis you plot the energy of each electronic state, again in units of the Raka parameter B. So obviously here at the origin, where delta is equal 0, what you have here is the spectrum of a free ion. Yeah, so that is the zero field free ion limit. Then you start to turn on the ligand field, and the various states of the free ion will evolve into the various terms that arise in the complex, in just the way I've described it. Now, for not all, but a number of the possible dn configurations, there is a critical ligand field strength at which point the system is switching from a high spin configuration here in the weak field regime to a low spin ground state. Now, since in a Tanabe-Lugano diagram all state energies are given relative to the ground state, so there is a sharp break in here in these diagrams, and they look discontinuous, and then the evolution of these states continues. So that so that is the Tanabe-Lugano diagram, and it tells you a lot about the electronic structure of transition metal complexes and their spectroscopy, and hence the Tanabe-Lugano diagram should be on everybody's desk. It's your best friend as an inorganic chemist. Now look at it. So for example, that is a D2 system. That is a Tanabe-Lugano diagram for a D2 system. And you see there are already quite a number of states that arise. Yeah, for the free ion you have like a triplet F ground term, and then you have singlet D, triplet P, singlet G, singlet S, and so on and so forth. And they evolve into quite a number of molecular terms. Now, in terms of the spectroscopic properties of it, now you have to realize that electronic transitions are strongly forbidden unless the states that are involved have the same total spin. So we have a triplet T1G ground state in an octahedral complex, like here vanadium hexaco, and now you look for other states that have triplet multiplicity. Now if you look at the Tanabe-Lugano diagram, there is a triplet T2, there is a triplet T1, and then there is a triplet A2 very high in energy. Now if you look at the absorption spectrum of hexaco vanadium 3+, you will find indeed 2 peaks. And now you use the Tanabe-Lugano diagram and you say, oh, this got to be assigned to triplet T2G, this got to be assigned to triplet T1G. None of the singlet states will contribute, or they will contribute tiny, tiny, tiny peaks once you blow up that spectrum. Now that is something that you wouldn't have been able to come up with easily if you did not have command of ligand field theory. You can also see from the Tanabe-Lugano diagram, not directly, but many of them label the electronic configuration that the triplet A to G, here this one, that corresponds to a double excitation. Now, say you have like a nice weak field ligand where you would be able to observe that state, and then you do your TD-DFT calculation or something like that, you would not find that state. It's simply not there, because TD-DFT doesn't include any double excitations. If you're not aware of ligand field theory, you completely miss it. You might like misassign the entire spectrum just because you used a deficient theoretical method. That's why it is so important to have command of these things and to really understand what they mean, because they guide you greatly through the chemistry of these transition metal ions. You will also notice that there are a few states here that are basically independent of the ligand field. Yeah? So what are these states? These are simply states, they're singlet states. These are spin flips inside the T2G shell. So their energy basically doesn't depend on the splitting of these d orbitals. It's nice, it's easy to understand if you know a little bit of ligand field theory. So now you can go basically through all of the dn configurations and go and look at their properties. For example, the very busy Tanabe-Lugano diagram of D6 ion tells you that in the weak field limit you have a quintet T2G ground state, and so if you want to go to the absorption spectrum, you will find just one other quintet state, which is a quintet EG state, and that is the spectroscopy that you observe. That is not a particularly pretty spectrum, but in general, that is what you observe is a single quintet T2G to EG transition that might be split by low symmetry effects. Now here's a classical spectrum. That is a classical spectrum of D5 ions. So high-spin D5 ions are set in the weak field limit that has a sextet A1G ground state, all electrons paired. Now if you apply a photon you will see there is no other sextet state, and that makes sense because all of these electrons have the same spin, so you cannot transfer any of the electrons to another orbital without changing its spin. So there are no spin-allowed transitions in high-spin D5 systems, and hence their absorption spectra are incredibly weak. So this is the classical absorption spectrum of hexaco manganese 2+. That Klicksby-Jorgensen, one of the famous pioneers of ligand field theory, actually measured point by point. So each of these things is a measurement that he took. Yeah. Parenthetically, so this is the way you measured absorption spectrum back in the, I don't know, 1950s or so, 1960s. He was actually reported to like tables of absorption versus wavelengths better than these graphs, but that is obviously a very strange taste. Anyway, so what that tells you, the molar extinction coefficient here is just 0.03 for the highest peak. Yeah? So it's tiny, tiny. That is why sextet S-state ions, especially those of manganese 2, are usually colorless. You understand that on the basis of ligand field theory. Now obviously all of these transitions that you see here, they must be spin-forbidden transitions. And using the Tanabe-Sugano diagram, you can easily assign those to quartet T1G, quartet T2G, that is quartet A1, quartet EG, very sharp feature, and then there is another quartet E and quartet A2. Perfect. Ligand field theory describes all that really perfectly. You can get even numbers out of that. You can fit now the B parameter and the delta parameter to all of these peaks that you see, and that is when you extract the ligand field splitting experimentally. It takes as much as a ruler. It doesn't take a high-powered computer, it doesn't take a complicated theory, all that it takes is a ruler. Yeah? You will also notice that if you look more deeply what these states are, that these states are spin-flip states that do not involve excitation from an electron from the T2G shell to the EG shell or vice versa. And that is the reason these bands are so narrow, because they're not associated with any vibrational progression. Now we would need to go a bit deeper into the theory of optical spectroscopy to understand that, but it is something that you understand immediately from the Tanabe-Sugano diagrams. This is all really sweet. Now, the Tanabe-Sugano diagrams are fantastic principle, the thing that brings order and meaning into a vast array of experimental data. Now we need to talk about a few more aspects of coordination chemistry, and one of it is the Jahn-Teller effect. So now, so far, we have talked about just octahedral complexes, and we found out that many of them have orbitally degenerate ground states or excited states. So states of T or E symmetry. Now, what happens if an electron can occupy one out of a couple of degenerate orbitals? So let's look at the D7 configuration. And in the D7 configuration, if it's low spin, then there is a single electron that occupies the EG shell, and it could occupy either the x squared minus y squared or the v squared orbital. Now, what the Jahn-Teller theorem is telling you, that nature will spontaneously break that degeneracy in order to force a decision where that electron has to go. Now that could happen in two ways. You can, for example, elongate the octahedron, which would stabilize the dz squared orbital over the x squared minus y squared. That would make the electron go to the v squared orbital, or it could compress along one of those axes, along the z axis, and then the electron would end up in the x squared minus y squared orbital. The Jahn-Teller theory will not tell you which of the two happens, or whether there is another distortion, say trigonal distortion, that lifts that symmetry. It will simply tell you that there always will be a spontaneous distortion, such that as an actual matter of fact, the electronic ground state or an electronic excited state will remain non-degenerate. So nature hates degenerate states. I don't know why, but that's just the way it is. It's actually interesting to go back to the original literature and read the paper of Jahn-Teller. You expect the thing to be like a complicated, like powerful, deep mathematical analysis, and you will find now it wasn't. It was they were simply going through the points group one after the other, and we're finding that it holds always. Yeah? The Jahn-Teller theorem holds for nonlinear molecules. For linear molecules, there's the equivalent of the Jahn-Teller theorem, which is the Renner-Teller theorem. You would think that in coordination chemistry, linear molecules are irrelevant, but that's not true. There are indeed two-coordinate complexes with absolutely fantastic properties, and they surely show Renner-Teller effects. I don't know if Michael and others will talk about these, but they are highly interesting molecules. So that is the Jahn-Teller effect, and we can now go back to the spectrum of titanium hexaquo 3+ that I showed at the beginning and understand why that band shape is asymmetric. In this case, we have even two Jahn-Teller effects. We have the Jahn-Teller effect in the ground state, and we have the Jahn-Teller effect in the excited state. Yeah? So in principle, we have a very complicated system. Now, which of the two Jahn-Teller effects will be stronger? And that is actually interesting. I jumped a little bit ahead of myself in saying that the interaction of the electrons in the EG orbitals, or the most destabilized orbitals with the ligands, is necessarily stronger than the one in the less destabilized orbitals. Yeah? If I jumped a little bit ahead of myself, this is sigma antibonding, this is pi antibonding. And the stronger that interaction is, the stronger the Jahn-Teller effect will be. Yeah? So if you have essentially non-bonding orbitals, the Jahn-Teller effect will be very weak, but it will be present. So what you mainly see here is the excited state Jahn-Teller effect in the hexaquo titanium. Yeah? So that splits the symmetry like the degeneracy of the doublet EG term, and that is what you observe. Yeah? So that is interesting. So we have octahedral complexes, we have multiplets, we have Tanaka-Sugano diagrams, and now you can go through all of the coordination geometries and ask yourself, what are those orbital splittings that you have in those coordination geometries? So we talked at length about octahedral complexes and their splitting into T2G and EG orbitals and everything that arises from it. Now, if you take away one ligand here from the z-axis, you go to a tetragonal pyramidal complex, and what happens then is that there is a repulsive interaction missing from the z-axis, which will stabilize the z-squared orbital and the xz and yz orbitals. If you remove that second one, that trend will be further, and that z-squared orbital will go further down, and it may or may not cross the energy of the xy orbital. Now, for a trigonal bipyramidal system, you have a totally different ligand field splitting, where your lowest energy orbital is a degenerate set of e orbitals xz and yz. The second set of e orbitals is xy and x squared minus y squared, and highest in energy is the d squared orbital. Now, for a tetrahedral system, you have a splitting that is also interesting because it's the exact opposite of the octahedral splitting. And then you have lower energy x squared minus y squared and z squared orbitals, and higher energy x, y, xz, and yz orbitals that belong to the T2 configuration. Now, it has been another triumph of ligand field theory to predict that the splitting in a tetrahedral complex for a given ligand is -4/9 of that of an octahedral complex. So, roughly speaking, the ligand field in a tetrahedral complex is by its nature half as large as in an octahedral complexes. That is why there are next to no low spin complexes with tetrahedral symmetry. So it's a nice thing that you also understand on the basis of ligand field theory is why are there no low spin complex tetrahedral symmetry? It is because the ligand field splitting by its nature is very small. Good, and now you can take advantage of that and start to do chemistry and spectral correlations. I will quote one example here and show you an application. And an application that was done by Ed Solomon and his co-workers. And he first went through model studies and he studied high-spin iron 2 complexes. And he studied iron 2 complex. In an octahedral complex, you have quintet T2G ground state, and then you have quintet EG excited state. So that will be subject to Jahn-Teller effect. So what that leads to is that effectively in those 6 coordinate complexes, you have an absorption band at around 10,000 wave numbers split by about 2,000 wave numbers, and that is the signature of the 6 coordinate complex. Now for a tetragonal pyramid, like you can work through the Ligand field theory and find out that you have a band at 10,000 and there will be one at around 5,000 wave numbers, and then I'll just let me. Okay. Now for a trigonal bipyramid, you will have one band at around 7,000 wave numbers, and for a tetrahedral complex, you will have 2 bands at around 5,000 wave numbers. So there are nice spectral correlations. So these are low energies. These are not absorption spectra. These are magnetic circular dichroism spectra. That has practical reasons because the MCD is much nicer to measure in the near infrared than the absorption spectrum. So if you suspect you have like interesting signature transitions there, then find yourself somebody with a near infrared MCD spectrometer, like your friendly colleagues at Mülheim have, and you can measure these things. With an absorption spectrum and spectrometer will be hard. Okay, now we have structure spectra correlations. Let's look at an example of an enzyme. These are risky dioxygenases, and now you start to get serious in that business. So we started with like very elementary Ligand field theory, and we're now at the interpretation of actual experiments on metalloproteins. So you see how quickly it becomes useful. Now these enzymes, as I say, they have a risky center that serves as electron transfer. That's a 2-sulfur iron sulfur side. And it has an active side that does the chemistry. And that chemistry is hydroxylation chemistry. We will not look at it in detail, but it is reactivity that you often observe in these mononuclear non-heme iron enzymes. That iron side here is very typical. It contains like a facial triad of 2 histidines and 1 carboxylate and an external ligand as well. That doesn't matter for our purposes. Now, if you study the spectroscopy of those, you can study the holoenzyme in the absence and presence of substrate, and it will not turn over before molecular dioxygen is added. So obviously that holoenzyme here has contributions from both the risky center and of the active side. But you're only interested in the active side. So you can do a bit of chemistry, you can add cyanide or EDTA or so to remove the active side iron, and you end up with the MCD spectrum of the risky center. That looks funny, but you don't need to be interested in that because you can simply subtract it here from the holoenzyme, and you end up with the MCD spectrum of the active side. Now look together with me. In the absence of substrate, you have the MCD spectrum that shows a band at around 10,000 wave numbers split by about 2,000, so this is an octahedral side. Now when we add the substrate, you have another band growing in here, so you have a band at around 10,000, 12,000 wave numbers and one at about 5,000 wave numbers. So that must be a tetragonal pyramid. Or in other words, that active site has lost the ligand upon substrate binding. Now that is, of course gives you a hint at the early stages of the reaction mechanism. Because if you look what happens here, you started with the resting side that is a 6-coordinate iron 2 side. And it's great that it's 6-coordinate because it's coordinatively saturated and it won't react with dioxygen in the absence of substrate to give you Fenton chemistry that would damage your protein. So, but when the substrate binds, it opens up a coordination side, and then dioxygen can bind, but it can only bind if substrate is there. And then the follow-up chemistry happens. You can form a hot species, which at the end of the day is always an iron 4 oxo species, and then hydroxylate the substrate. But you can see how you can use a combination of spectroscopy and ligand field theory without even doing much high-powered computation to obtain insight into the early stages of this reaction. So that is cool. I mean, and that I think hopefully shows you how useful ligand field theory can be in order to bring meaning and order into your data. So now that I convinced you how great ligand field theory is, I tell you how not great it is, because it was already Klicksbuhl-Jürgensen who said, and he invented it, who said, like, personally, I do not believe much of the electrostatic romantics many of my colleagues talked about. So what I just brought to your attention, that was the electrostatic romantics. Yeah, the idea that a ligand in a transition metal complex is simply like acting as a point charge that splits those d orbitals apart. And rather than making any theoretical arguments, I will call an experiment, and I'll show you an experiment that is kind of very telling in that respect. This here is the EPR spectrum of copper tetraimidazole. Copper tetraimidazole 2+, that's a copper 2 complex. It's a D9 system, has 4 imidazole ligands, and it has an EPR spectrum that, broadly speaking, follows the prediction of ligand field theory. It's a signature of quadratic planar complex. It has a G bulge, a G parallel, and a G perpendicular, but here, superimposed on the G perpendicular signal, there's an interesting structure. Now, that interesting structure, where does it come from? It's not the hyperfine structure from the copper. Now, you can do an experiment to convince yourself where these signals are coming from, and you can label your imidazole with N15. You will then see that this pattern here is changing. So by that experiment, you prove that this hyperfine structure here is coming from nitrogens. Now, you can only have hyperfine structure from nitrogens if there is unpaired spin density on those nitrogens. Now, you look at what ligand field theory tells you about the D9 complex, and it will tell you that it is the x squared minus y squared orbital that is highest in energy, and according to ligand field theory, it will look like this. It would be a pure metal orbital. This experiment tells you that that's not correct. The actual historic experiment wasn't done on copper tetraimidazole, it was done on iridium hexachloride, but the message was the same. There is something that the physicists at the time called the transferred hyperfine field. But what they really wanted to say is that there is unpaired spin density on those ligands, and if you stay in the molecular orbital picture, that means that this is not realistic. So you need a better theory that includes ligands explicitly. That is something, of course, that if you're a physicist, you hate that because you have to deal with all that chemistry stuff. But when you're a chemist, you like it because you have a strong feeling that your ligands are not just point charges, but that they have an internal electronic structure, and that internal electronic structure of the metal, of the ligand that matters, of course. Now, at that point, we start to marry the quantum chemistry that I talked about in the first lecture to the ligand field theory that I talked about now, because that theory that explains these things, even qualitatively right, that is molecular orbital theory. Now, in a nutshell, how do you construct molecular orbitals? So you have constituent orbitals of the fragments, and when they come together, they form bonding orbitals and anti-bonding orbitals. You should notice that the bonding combinations are always less stabilized than anti-bonding combinations are destabilized. That accounts for the fact that if both of the fragment orbitals are fully filled, so that all of the molecular orbitals are filled, the overall interaction is repulsive. That's why rare earth ions don't stick together, or at least not very strongly. So that is a homopolar bond if the energy of the fragment orbitals is identical. If they're not identical, it's a heteropolar bond, where the bonding combination mainly reflects the component of lower energy, and the upper component, the anti-bonding component, mainly reflects the contributions from the higher energy one. Now, there are orbitals of different type. you have sigma bonding orbitals, pi bonding orbitals, lone pairs, and you have sigma anti-bonding and pi star anti-bonding orbitals. Importantly, without doing any calculation, the formal definition of the bond order is 1/2 the number of electrons in the bonding orbitals minus the number of electrons in anti-bonding orbitals. Now, if you look at the molecular orbital diagram of an octahedral transition metal complex, you will find that it already looks pretty complicated, and it's also a reason why it was more fun to do ligand field theory, because you have to deal with quite a lot of stuff. And now, these are the orbitals that arise in the transition metal complex. So you start from the metal on the left hand, has metal D shell, a metal S shell, and metal P shell, and then you have ligand S and P shells, depending on what the ligands are. Here it's just like 6 halide ions, and there is a substantial number of molecular orbitals that arise from that. Now the important point is that according to the valence shell ionization potentials of metals and ligands, these metal d electrons effectively are at higher energies than the filled ligand orbitals. So that means you form heteropolar bonds in which the anti-bonding components are mainly metal d orbitals, and these are exactly then the orbitals that ligand field theory is talking about. Yeah, so it is these shells here. These are mainly metal orbitals. They're anti-bonding mostly, and they have the same symmetries as the ones that were predicted by ligand field theory, and they come in the same order. So that is good. Through that bonding, some of the electron density is transferred, obviously, from the ligand to the metal. We call that covalency. It's a big issue in transition metal chemistry. I don't think we will have enough time to dig any deeper into it, but covalency, to the extent that metal and ligand orbitals mix, is a major factor in controlling the properties of these transition metal complexes. Here we only stay on a superficial level and will connect the molecular orbital theory to ligand field theory. Now obviously we can explain our experiment, and we can explain it in a very easy fashion. So if you now do whatever molecular orbital calculation on copper tetraimidazole, you will find that the singly occupied orbital is indeed, has a contribution from dx squared minus y squared. And then it is anti-bonding with the sigma lone pairs of the imidazole. Now, in principle, if you want to stay in that picture, you can even estimate from that splitting here between those peaks the amount of ligand character in that orbital. Now, this is in direct contradiction to what I told you before, is that you cannot measure orbitals, and you really cannot measure orbitals. So when I say that you can measure the amount of ligand character in this orbital, that implies a specific model. You can do whatever you want as long as you're absolutely crystal clear on what you're doing here. Yeah? So now we're creating a model of molecular orbital theory that is entirely sufficient to explain this experiment. It will be entirely insufficient to explain other experiments. So if you work yourself the way from many electron states down to orbitals, you can gain a huge amount of insight by looking at these orbitals, but don't do it in a naive way. At the end of the day, states, and I only say that because I can arrive there by arguing with states all day long and then simplify it down to the point where I can point to this orbital and say, look, this is really what explains this experiment. No? So that is nice. And molecular orbital theory then, of course, also explains the spectrochemical series. And in order to do that, we look at a typical weak field complex and a typical strong field complex. Now, you look at the molecular orbitals of ferric hexachloride, you will find that the 5 d-based orbitals, that is a good language to say these are metal d-based orbitals that are just diluted with ligand orbitals. you will find that the EG orbitals are sigma antibonding with the ligands, whereas the T to G orbitals are pi antibonding with the ligands. And that is all good. And normally, since the sigma overlap is stronger than the pi overlap, these are higher in energy than these. So far, so good. Now, if you look at a typical strong field ligand, like chrome hexacarbonyl, then you will find that the EG orbitals are still sigma antibonding with the ligands, but something funny happens in those T2G orbitals. And the T2G orbitals, and you maybe need a bit of a trained eye to see that, these are the carbonyl pi star orbitals, so they're empty in the free ligand. And they have a bonding interaction with the T2G orbitals, yeah? And that is called metal ligand pi back bonding. And I'm sure you're familiar with it from your organometallic lectures. So what happens here is then that a filled metal T2G shell is interacting with an empty CO star orbitals on the ligand. Now what that means in terms of the bonding is clear. In the middle of the spectrochemical series, we have the pi neutral ligands that only have sigma orbitals to bind to the metal. And so the T2G orbitals are basically not touched, they're non-bonding. The EG orbitals are sigma antibonding. Now to the left of the spectrochemical series, you have those ligands that form strong pi bonds with metal, and that means that the T2G orbitals are strongly destabilized by that pi direction. It doesn't mean that the bonding is weak. So a weak ligand field splitting absolutely doesn't mean that the metal ligand bond is weak. On the contrary, right? These things form strong bonds with the metals. It's just the ligand field splitting is strong, is weak because the differential splitting between pi and sigma is small. Yeah? So this is why iodide and sulfide are to the left of the spectrochemical series. Yeah? And to the right of the spectrochemical series, the really, really strong field ligands, they are pi back bonding, and what happens here now is that the interaction of the empty ligand pi star orbital with metal orbital presses down these T2G orbitals, and hence the apparent ligand field splitting is very large. So I think it is not worthwhile to start the next subject. There is quite a bit more in your lecture material, but I think I've tortured you enough this morning. You deserve a break. But before we run for lunch, we convene outside and take the group picture, please. Yeah, so I will end now. Those of you who choose to hear a bit more advanced material, I'm here tomorrow afternoon to talk to you about effective Hamiltonians. And otherwise, I wish all of you a lot of fun in your ORCA tutorials this afternoon, where you can put all of what you heard this morning into practical use. Thank you very much.